Oh, I emailed Tom last night about missing that lab kit in,
Oh yeah.
and he said that he's gonna try to find something to make it up. He had to get permission to bring his sources yesterday, so
Okay.
that's why he said that we should email him.
Yeah, I'm gonna email it too. 'Cause I can't yet. What did he say? Just on our next lab or our next lab, we're gonna have something.
No, he said that we'd try to find something.
Okay. Wait, I'm gonna email it to you just so. He probably doesn't know us all enough yet to know who wasn't here.
Okay. Everybody get their attendance. I got you, Jack.
Thank you.
You're welcome. Okay.
Can you do my attendance, please?
Is that Jennifer?
Yes.
Yes, I can, Jennifer.
Thank you.
You're welcome. Jennifer? Got it. Oh, it didn't save yours, Jack. Let me save that. And Kyle, it looks like it didn't save yours. Do you want me to do it for you?
I
Okay, I'll save it.
my internet on my phone will just load and load and load and load.
I don't mind doing it. I just want reminders so that we have the right attendance.
Thank you.
No problem. Okay, so we're going to talk just briefly the lecture that is on Moodle from yesterday. The first half of it is just review of what we did Wednesday. So we're going to jump in here at slide 9. I'm just going to talk just a little bit, and then we're going to go through some calculations. And I've gotten a couple questions on the worksheet on the scattering equations and that chemical equation stuff.
I couldn't find my notes on that.
Okay. It was supposed to be a review from chemistry, just to have you guys have that fresh in your mind, but we will go over it. That is not a problem. And we'll make sure that it's fresh on everybody's mind. I hope not, but we'll go over it. Okay. So, chemistry. Do you guys remember talking about Coulomb forces? Okay. Okay. All right. So the Coulomb force is essentially what holds all the pieces inside an atom together.
By charge.
No, because you've got neutrons that don't have a charge, and they have a force that acts on them too. Okay? And when you have all of the things inside your atom to make it happy and balanced, and all those subatomic particles are copacetic, that force will actually repulse anything else that tries to break into the atom. So it both keeps everything together and keeps it from changing. There's also a strong force that does the same thing. Most atoms, the strong force is stronger. But when we start getting into our heavy nuclei, like what we use in the nuclear industry for fuel, these two forces have a balance, okay? Because that repellent and attractive force, the balance between the Coulomb and the strong force, is carefully balanced, it's easily disturbed if something like a neutron slams into that atom, okay? But because there is a force that is resisting change, that neutron does have to have enough energy in the first place to start a fission reaction. That is between 5 and 6 MeV. Oh, I'm sorry, guys, online. I didn't realize my background image was on. You can't see anything. There you go. Just now noticed that, sorry. So, you have to put in enough energy to actually create an excited state. What were the two reactions we talked about that end up with an excited state nucleus? We have, yeah, our scattering reactions, right? Okay. So, because of our discussion on binding energy, if a heavy nucleus breaks up into fragments, the sum of the energies of the fragments would be less than the energy of that whole nucleus, right? Because the pieces and parts have a different energy than the whole nucleus. And so when we break it apart through fission, and this is how we get our fission energy, right? The difference between these, that energy that's essentially not accounted for in between the two, is what comes out in our fission energy. We're going to talk about this in units of mega electron volts, okay? And it's about 1 million more times more energy than burning an atom of coal to fission an atom of uranium. To provide our fuel with enough energy to overcome that Coulomb force that's holding everything together and resisting change, we have to use that 5 or 6 MeV neutron, right? Neutron absorbed by uranium-235. We get unstable uranium-236. It's going to distort as it starts to overcome that Coulomb force that holds everything together until it splits into 2 fission fragments and multiple neutrons. Here they use krypton and barium. Every fission reaction is going to have a slightly different set of fission fragments that are released. And the 2 A numbers together are going to add up to uranium-235. Yeah, Joe.
Every different fission will have different products, or every different kind of fission? Like fission from one fissile atom, will fission from 235 always have krypton and barium, or it's totally random?
No, it's not totally random. Let me pull up a graph real quick. There is a distribution probability.
So there is a way to tell what the product, like what the end product is gonna be, but it's like not a for sure.
Right, so there's this distribution that looks like this. Did Mike ever show you guys this graph?
Yes.
Yeah.
Okay,
I never understood it.
so this side is your percent yield, and this side is your mass number. So a very, very small amount of the time, you could produce literally any mass number between 70 and 170 in your fission fragments. The vast majority of the time, you're going to produce fission fragments with an A number between 94 and 96, right here at the top, and between 130 and 137. And you'll produce one of each, because together that adds up to 235, right? So there are some that are common, and they list these most common ones right here: xenon and beryllium, cesium, barium, lanthanum, I don't remember that chemical symbol, strontium, zirconium, well, strontium decays to zirconium. So strontium, xenon and strontium have some very special properties, and we'll learn about those when we talk about fission fragments more later in the class. But what this is saying is the highest probability is going to be one fission fragment with an A number between 95 and 96 or 7, I think it is, and between 130 and 137. You're going to have one of each of those. And the numbers that you can get larger, right? You can go between 90 and 110 and between 130 and 170 with a 0.01% yield, but your most common yields are going to be right there. Does that make sense? So you're going to have slightly different fission fragments, but they're going to stay in this little group.
I think the yield percentage.
How come?
I don't know. I feel like I want to be thinking energy level or something like that.
You're going to get roughly the same amount of energy from fission every time you get a fission, because you're having the same reaction over and over, right? So rather than thinking of it as energy, this is for uranium-235 fission, and honestly, this is for thermal fission, right? This is for thermal neutrons, which we know because uranium-235 doesn't fast fission, doesn't have a very large cross-section for it. So you already know the energy, you already know the reaction. This is telling you how likely you are to get something out of that reaction. Okay?
So is that amount of energy, 5 to 6 megaelectron volts, is that like, that's just for thermal fission?
Yes. Mhm. So, first calculation. What is the binding energy per nucleon of uranium-238? And what is the binding energy per nucleon for an excited uranium-238? that's our constant to turn it into, from AMU. MEV, right?
What's that?
900 and, 31.
131.
Let me make sure. But I think that is correct. $931.5 MEV per AMU.
Heavy duty excited.
So this is our binding energy for U-238 plus one extra neutron, right?
Okay, so is it per nucleon plus the energy of a neutron?
So you're gonna do your straight binding energy for U-238, just like we did for U-235.
Yeah.
Then our excited state is U-238 with an extra neutron. So you're gonna add one more mass of neutron to your mass of all the components. Subtract your U-238 mass and divide by
238.
Okay, so. Right, so A and Z number. Okay, so that's your Z. No, this. All of that. Which is good, because then we can make it easier, right?
Oh.
And I should make the note that I took this equation, I took a screenshot of the DOE handbook. All this note is telling you that the excitation energy of our neutron was 4.8 MeV. So it's around that between 5 and 6, right? You don't actually need this information for what we're doing here.
Just saying that was thermal.
Just say, we have an energetic enough neutron that we can create fission.
And then for the neutron, we use the 1.008666 for bond one.
That's correct. The AMU. value.
And
Yes.
it just has a U right
Is it gonna be like a lot more?
So given how small our numbers are, it is a lot different, but in the grand scheme of a lot, it's kind of a small difference. Sorry, that's a confusing answer. Like, I think it's a lot because we're dealing with values that are, 0.0005 AMU. To answer your question, Katie, U is the abbreviation for AMU.
Oh,
FT is the abbreviation for feet.
what in the world?
S is the abbreviation for seconds.
It'd be so much harder to write AMU, like all the way down.
I know, right?
Just have to make it.
Did anyone calculate the binding energy per nucleon for uranium-238?
Almost there.
Okay.
7.8.
You what?
7.8.
7 point binding energy per nucleon?
I got 7.572.
Who's wrong?
Okay, let me check my math, because I got something different than both of you.
I got 7.79. That's what I got. Is it?
No. You know why, yeah? Because you're wrong.
I think so.
No,
I have a question real quick, Mackenzie.
Yeah.
So the rest mass of a neutron and the electron, will that always be a constant?
Yes. And the rest mass of a proton as well.
Yeah, so those numbers will never change.
Correct.
Okay, thank you.
You're welcome.
Okay, I didn't realize that.
how far out with the decimals are we going? I wrote
4
all.
decimals.
Oh. But too many. It's fine, you can be more accurate.
Did you get to the binding energy, 7.9 something?
I got 7.8 for nucleon. Yeah.
But 7.57 and 40.
Okay, that's what quarter, that's what it's on there.
That's what I thought was 7.57.
So you just do a 931.5 over 1. And then square it.
No, 931.5 is squared.
Oh, so you don't have to do anything with that?
Correct.
So it's still over 1 though.
It's over 1. Correct.
Oh, I got negative 135,423.
So do you remember when we discussed that when we're talking about fission, we will probably never get a negative energy
I know.
answer? Okay.
This is a new discovery.
Okay. Porter, what did you get again?
7.5720.
And what did you get, Jack?
Well, I must have done it wrong, but, so for per nucleon, I
Mm-hmm.
got basically 7.8, because like 7.79.
Okay, I have a slightly different answer than both of you still.
I got 7.5701.
Hold on. I'm
What'd you
on
get?
I ended up with 7.56997.
Hey, that's damn close.
Now round that 6 up to a 7 and that's the answer. Yeah.
I don't know what it did wrong.
I did that equation, but where do you add? So right now, I'm just asking, did we calculate the binding energy per nucleon of uranium-238?
And it's 935.1 megawatt.
931.5
Ooh,
MeV per AMU.
maybe that'll change it.
So if we're off by like that, so you got 7.566 and I got 7.57.
So that's fine, because I told you I'm gonna grade out to 2 digits. So we basically got the same answer. That's why you gotta make sure you're carrying out to 4 all through the math, so that you're not rounding so that your answer looks wrong.
I'm carrying out the whole thing from here.
Yeah, which you can totally choose to do, and you'll get closer to that answer. So, still working, Kyle? Sam, did you get an answer?
So I got 7.5694.
Yeah. I got pretty much what Porter got.
B for nucleon.
Yours is the closest to mine so far. Amber? Oh, sorry. We're just stop here. Stop at 238, finding energy for nucleon.
Oh.
Amber, did you get an answer? Okay. And Marcus and Jennifer, did you guys?
I got 7.57.
And Caden, you didn't get.
I got negative 135,000.
So I don't know how to do the plus n, I guess.
Okay, we'll do that in just a second.
Oh.
Right now, for this moment, somebody who thinks they got the answer right, want to walk us through it.
I'll do it.
I'm gonna go with Kyle.
No, I'm just kidding. You go to-
Caden didn't get the right answer.
7.57 or somewhere around there. That's not right.
But the final answer is 7 something, right?
Yeah, I got it.
7.56, and then a number above 5 after
Am I
that.
really going up there?
Yeah.
Well, what was
Once I got
your,
that, I did that.
what was
If
your
that's
final
not right,
answer?
it's always gonna be wrong.
My binding energy, total binding energy
Yes.
was 1,801.65.
This is.
So I got,
Oh, no.
Your neutron.
I got 1801.7946.
On mine it just says CMP. So MP.
Can I borrow your pencil?
What'd you get for binding energy?
I know, I need to write it up.
I don't have
Can I borrow your pencil?
Yeah.
I'm sorry, what'd you say, Joe?
What'd you get for binding energy?
The total binding energy I got was 1,801.6527 MeV.
This, this is what you did
Yeah, I
yesterday.
got.
And if that was the right formula, and she said, yes.
All right,
Because I was wondering about.
Well, let's go through it.
listen up. No, just kidding.
Remind me of Mike, had a Mike flashback.
That's it.
But he did it when everybody was like looking at him. He'd just be like.
I bet the other instructors loved that.
Hold him a wall.
Yeah. Okay, so we know that this. Oh, that's hard. Wow. Okay, so this equals Z. Do I have to do this? Everybody's got the formula?
Let's go ahead and write it and work from it, just to
Okay.
make sure we're all making the same mistakes.
And then P plus M. You're right. E got that right. Plus A minus Z times mass neutron at rest. And this is going to be constant.
And Adam, you minus your Adam.
I just haven't got there yet, but yeah. Minus the atom. So
And that,
choose the
yeah.
point. Oh God, I don't know if I remember. Hold on, I'm getting. 1.0076 plus 0.005485 plus 146 1.008664.
Did you say 664 or 665?
664, but that could be incorrect.
I'm just thinking I might have the wrong constants.
I got the 661.
So
Well, that's a
If-
mass
the neutron rest mass
that I just
is
did.
1.0086649. So when we round, if we stop at that 4, when the next digit is a 9, what does it have to be?
A 5.
A 5.
So that 4.
Well, I just didn't round it because I didn't round it
Also,
until the end.
But if you stop writing digits, you round it. And just right now, you just rounded incorrectly. So it would be a 5, or it's a 4-9.
So that probably changed my thing about like.
Just a little, yeah. But
most-
now we're finding out where some of our differences are, right? And showing how important it is.
So what's
to not
right or
round.
wrong? You'd rather see that go to a 5?
If you're gonna stop at that digit,
Oh,
you
okay,
have to round it to a 5.
okay.
If you wrote 4-9, the next number after the 9 is a 1,
Right,
right? So it doesn't round up.
right.
So you could stop at the 4-9, but if you stop at the 4, you actually have to round it to a 5.
I think I just use like the same figure, so I don't know why. Anyways. So then for here, I don't know if you want me to continue. Do you want me to
Yes, I
continue?
do want you to
Okay,
continue.
so, this is gonna be the same.
So I think that you might have transcribed your proton mass wrong too. 1.00727.
I just didn't write it. Yeah. And then 927. This is hard to copy like while I'm trying to do this quickly. 5, 4, and then. So then that takes away this. And then plus 147.2649. And then minus the 238.0507. And then when you do that on the handy dandy robot calculator, you should get something, or I got something.
And then just one more time, sorry, right here. This is 050788.
Okay,
So
so
if you
8.
round here, yeah, here we're 8.
Miss McKenzie, could you type this in
No.
Moodle? Because I can't really see the board that good.
Yes.
Thank you.
0.
Figured out where I messed up.
Yeah, I was doing 238 instead of the actual mass we got.
Okay. Do you have a question, Joe?
I didn't put the 146 there, I just had the 1.008. I subtracted 238 from that, so that's probably why I got it.
Oh, yeah. Probably.
Oh, I do have a question.
Yeah, because then.
Give me 1 second, let me type this out for those
So do you?
on Moodle, and then we
so
will
you times the.
answer your
that
question.
proton, Or, sorry, the neutron.
Right,
Yeah.
after, so this is 238 minus 92, that's 146, and that's the neutron, is that.
Then minus the 238.
So then you multiply them, and that's what you get, and then you minus the atom,
Mass
the
number.
238 point, well, it's in your nuclide.
Yeah. Okay. Yeah, that's right. It looks,
Oh, yeah.
I messed that up.
I still got 1.93416. Oh, you did.
That is that.
Oh.
But,
And
obviously,
then you do the-
Mackenzie pointed out my rounding errors, so probably like a millionth of a, or tenth of
I
a
didn't
million.
round it all and I got 1.934.
Which I guess that's not really splitting hairs in nuclear career stuff, but,
And then.
Everybody good to this point?
Can you guys see that online?
So then,
Yeah, I can, thank you.
Okay,
can I erase that?
so, let
Or do you
me,
wanna go over it?
no, you did great, Kyle. Let me,
Yeah.
okay. So, with not rounding, we've got 92 times 1.007276 plus 0.0005485 plus 146 times 1.008665 minus 238.0508.
Yeah, so that is obviously not gonna.
Yeah,
be
so
the
now
same.
without the rounding, what do you guys get for your mass defect, right? Because right now we're
'Cause
in
this
mass.
is different because I rounded differently, so
Yeah.
it's gonna be a little bit of
Like
different.
1/3 or 1.9319 or 1.932.
Well, you said we're only going out 4 digits from that, or on that, let me answer, on that one, on that.
This
final-
is, this would just be like, what, a 2 or 3?
I got that.
Or is there a difference?
I have a 1
That's what I
right
Okay.
here.
Yeah.
is a one,
And a 1.
and that's as far as like we should go.
That's as
Is
far as
the-
you need to go, yeah.
Is the one round, oh,
But the one, it'd be 1.93141414.
okay.
So I can just put a 1 here.
Just-
So just switch color for us.
Okay. I missed the number.
Yeah, but like, yeah, but I used all of the numbers that you were given, 6 numbers, I mean, that whole number, I didn't cut anything off. So.
Oh, well, no.
Or you took it pretty much the same.
Yeah.
Oh, not really. I didn't add in the resting house.
Well, it makes a little cloud, and then when it all
For her is, I'm using a formula that doesn't show the electron.
Okay.
Okay.
Looking at something.
Now we're here.
Oh, I got, you wanna look at the formula? Okay.
So those of you online,
So again,
Did
your
you
number's
get-
gonna be different by like
I'm
a
just gonna show her this answer.
1,000.
I would have had the right answer if I had the electron drawn.
Do the
So
round.
we're just
Now-
plugging in what you posted on here, right? The 92 times the 1.00727 plus. We're just plugging that stuff.
sorry, I couldn't hear you, Sam. Say that again.
Should have used his.
We're just plugging in the stuff you have up here on Zoom, right?
Yeah.
Because I ended up with 2.1271982.
Okay.
You're doing great, Kyle, awesome.
Yeah, I appreciate you standing up there.
Let's. Oops.
Yeah, I was doing it way wrong.
Thought we were gonna do a roast up here or something. What's that dude's name? It's like Alex, oh man, I watched one with Alex something, he's like a movie star.
Oh, I saw, I've seen the one with Justin Bieber.
Yeah.
They just sit up there and roast them.
See, that was a Caitlyn Jenner episode, huh?
They go after him too, it's funny.
Yeah, they go hard, they don't hold punches. Some of the stuff I seen on those roasts, I'm like, how can you say that on TV?
You guys pull your numbers up with that formula. Because I think everyone in class now has this answer, right? Okay, what's this unit?
AMU,
And
So what is this actually?
1.9341
What is it?
mass.
mass defect.
Mass defect.
And
So now how do we go from mass defect
Yeah.
binding energy.
You, just conversion factor.
Yes. So what is our binding energy of U-238?
Okay, so this, can I erase this now?
If you like, you could just make a new page.
Right here?
In case you
Oh,
want to
cool.
refer to that
Perfect.
page again.
So, we have 1.9341. And then without the one, our difference in rounding again, I got equals 1.521, again, rounding issues. And then I divided that by 238. Did I need that 0.0507 of this division? No?
For that one.
Okay, I don't think so. And then I got equals 7.5694 BE. I'm messing that up. Nucleon.
So with our corrected values, what did you guys get right here?
6484.
What I got? So
Okay.
6484. You click on this side of it, it gives you a quick eraser. So you know.
Oh, does it? Okay. So 6 what?
6484.
You don't have to do 238, the whole bottom row, and divide it just.
And then when you divide by 238, it becomes 75699.
Okay.
Everyone remembers the reason? No? Okay, what do you have, Lynn?
So when I times the 1.9341 by the 931.5, I got 1801.6142.
Did you use 1.93?
Plus or minus 66 on these.
Pretty much at the first two decimals, if you're within that.
Oh,
that's right.
Okay. Which, I mean, with all my rounding errors, I'm still within 2 or 3, honestly. Possibly 4.
7.57 would be okay.
Yeah, I mean, again, I would take that up to 4 numbers, but yeah, I mean, that's the same thing. If I round this, that's what that is.
Yeah.
I got
So I don't know, I guess it's kind of up for you.
I think it's because you went to 1.934. You left
Yeah.
out the,
Yeah.
like,
That's the
I had the
difference.
answer on here and I just put times. So it was like the decimals are drawn out already.
Yeah.
Yeah.
So if I round
Well, I feel like every time I
that,
do those long drawn out decimals on my calculator, something is fucked.
Yeah.
That's why I was only carrying out to like 4 or 5 going into the problem, and all rounding, I was just taking that number.
like, you're putting it on the board, and that's what you're using, and then I put that in my calculator, it's
Yeah,
gonna be
so-
different than what.
Another,
yeah, my calculator just used more digits than yours.
Huh?
So if you
Another-
guys rounded to 4 digits at that 1.9341, your answer is going to be 1,801.6142. Because there's a rounding. Right? So I had more digits in my calculator because it will go out automatically to 6.
So this is wrong, or is that?
No, they're rounded differently. So if you rounded to 4 throughout the math, which I will do on my solutions, when I do, like tests and homework, you're fine.
So yesterday you said to only round it on the final answer before, so now instead of the final answer, we're doing that on all of them?
You can. I'm telling you, you do not have to go out to more than 4 at each step.
But
If
if I'm
you-
gonna shorten it, I gotta round it.
If you shorten it, you gotta round it correctly.
Okay.
So if your calculator will take multiple digits, I'd leave as many as you can and round at the last step. You'll have the least amount of errors, right? Because every time you round, you have to make sure you make the right rounding rules.
But if we do it that way, we're gonna have a different answer than you are, because you just said you're only gonna round it out to 4 when you do your answers.
But if we have a slightly different answer, I'll be able to check really fast in my calculator if it was due to rounding.
So, and then you said that you're good with us out to the 2 places?
Your final answer, if it matches mine to the first 2, you got the right answer.
Would this be the right answer?
Oh, not that, I guess. That's not even the same thing.
Yep.
Sorry, online.
Nope, this right here. Yep. So my final answer here
Well, I'm not carrying to this one. I don't wanna get
was
confused.
7.5699, which would round to 7.57. So if at this step, you got at least those digits in common with me, you would have had the right answer, and I wouldn't have even had to check where the rounding happened.
Oh, I got the eraser on there.
Okay, so just real quick, thank you very much, Kyle. I'm gonna switch us back.
Roast is over.
You did awesome, Kyle. What we would have done to finish this problem is now you would have done the same thing, but you're gonna add a neutron to our excited state,
The rest neutron?
So we're just,
a rest neutron.
it'd be 147 instead of 146 for that.
So it would be our Z times the mass of a proton and the mass of an electron plus A minus Z times the mass of a neutron plus the mass of a neutron minus the mass of uranium-238 times our C squared, right, that 931.5 over 238 plus 1 neutron. There's an extra neutron in there now, right?
What's C squared?
Yeah.
This
That 931 is
Oh, that's all that is.
And can you explain the extra neutron in the denominator?
to become excited, we absorbed a neutron, right? So we're uranium-238 excited state, means that inside our uranium-238 is this neutron. So there's one more.
You have to divide it, to get the per nucleon, you're dividing it by 238 nucleons plus a neutron?
Right, so this is really 239,
Okay,
because we absorbed
okay.
a fission neutron. Yeah, see?
So when you're doing this calculation, can't you just treat that as U-239?
As long as you don't accidentally put uranium-239 mass here,
That's what I was wondering, like, how come you not put that?
because we're excited state uranium-238. We just have an extra neutron making that atom excited. We didn't become uranium-239. Because the energy that this neutron's at, we're not having an absorption reaction or a scattering reaction. We're gonna, or elastic scattering, we're gonna fission. So it's not
It doesn't
creating
become-
U-239, it's creating excited state U-238. Catelp and Joe. Okay, Joe.
What do you call that formula? Fission formula? The, what you just read?
This one,
Yeah, and the one below it.
this is binding energy for nucleon. Then this is just our conversion factor to go from AMU to MEV. This is constant right here.
Will you please
Is
not
that
erase that right now?
I will not erase that. If one of you guys takes a picture of that, could you
Can you switch?
send it to those of
And use them,
them who are aligned?
you gotta take a picture, they're actually swapped.
Pardon? Yes, you're right. MEV for AMU. I apologize. For those of you who are online, they're going to take a picture of this and they'll send you that. Yes, Jennifer, that's correct. There was some formatting where it should have looked like this on your sheet, right here, with that question mark being the nuclide.
Okay, thank you.
We'll come to your office hours if we need help on the last two questions.
Yes, I am gonna have to go do the rad lab for the first years. But then I'll be in my office from noon to 3, and I will gladly go over that since we ran out of time today, and I'm sorry about that.
Oh, I see what you did. The C squared is just off on the side, because that's what we're multiplying later.
Yeah, that's to convert it.
So is it the same steps?
Yes.
Mhm.
Oh.
Yeah, what you did was completely right, Kyle. We just fixed some rounding errors.
So C squared is just later. Okay.
Is that you on there just saying that's uranium?
The only difference.
Yes,
So
the
that's
math
gonna be
of
the
uranium.
238.05 only.
You
Is that a TI 84 you have there?
89.
Oh, you wanna sell it?
No, I don't. I've had it since college.
Really?
All right, I know I ran over. If you guys have questions, feel free to ask me, and we'll still keep going over this stuff in class.
and I get this.
Thank you.
All right, bye.